Okay, AC circuits. Some components will behave different, like inductors and capacitors, with alternating current than they do with direct current. And they tend to be frequency dependent, where direct current is essentially alternating current at zero frequency. So it means it doesn't alter. We characterize AC with frequency, phase, wavelength, and then we have the components, the reactance, impedance, and then resonance effects, and we combine them. So this was just a little simple thing showing generating AC voltage from this generator versus a battery, and switching between the two. I couldn't find much of an example. Okay, so let's talk about frequency. It's a measure of how many times per second the waveform changes polarity, and we represent it in hertz, named in Hz, named after Heinrich Hertz. It also has a period, which is the reciprocal of the frequency. It's how long in time it takes for the waveform to go through one complete cycle. Okay, so how many times it goes through a cycle per second is its frequency. How long it takes to go through a cycle is its period. Like a pendulum clock, okay, the period is how long it takes to go from one side over and back. The frequency is how fast, how many times it does that per second.
If we don't do anything to change it in the US, it's fed in at 60 hertz, right?
Right. For commercial power.
Yeah.
Now, like in aircraft and stuff like that, they use 400 hertz. And then Europe uses 50, I think.
But they use higher
voltage. Yeah. 220, 240, at least in England.
Most of Europe's the same, right?
Yeah. And funny plugs.
I don't know what country you go to.
Right. You get a whole set of adapters. Okay. Now, we also will talk a little bit about, and it'll come up later, phase, where I defined it as the fraction of a complete cycle of the waveform. And we can represent it in degrees, where we assume there's 360 degrees in a complete cycle. Now, that's not exactly arbitrary. If you envision watching somebody go by on a bicycle and you watch their foot on the pedal, it goes up and down as they're traveling, it's creating a sinusoidal waveform. So if you actually map circle over to a shifting thing, you can actually plot out by doing the value of the sine at each point you want to pick, plot it, you'll get a sine wave. And that's where that came from and why it relates to 360 degrees in a circle. And also it turns out in math, instead of using degrees, because they're nasty things and a lot of fractions and decimals, since everybody knows the circumference of a circle is 2 times the radius. So we came up with this thing called a radian. So we said a circle is composed of 2 pi radians. And it works out a lot easier in math, where you use 2 pi to represent a complete circle than doing degrees. And you'll see in a lot of these formulas coming up, you'll see 2 pi, which is where that came from. because they're all derived from using radians. They don't talk about the radians in any of the amateur radio stuff, but they do use the formulas, which has 2 pi in it, which is where it came from. But they do teach it in engineering school. And this is just showing what a 90-degree phase shift looks like between these 2 waveforms. So the peak of this waveform turns out to be at 90 degrees. And the peak of this one is 180 degrees. So there's a 90-degree phase shift between the 2. Okay, so the next thing we look at is wavelength. So if we've got a waveform and it's traveling through space, what we call free space, where it can travel at the speed of light. So we define the wavelength as how far it travels in some unit of distance, usually meters, in one complete cycle. We represent that with the symbol lambda for wavelength. So you get the formula that the speed of light, which is a constant, and we use 300 to make it easier, is equal to the wavelength in meters times the frequency in megahertz. And the reason we use megahertz is so we can cancel out the 300 million meters per second. So if we do this in megahertz, it automatically, let's just use the number 300 instead of 300 million. It just makes it easier to do the manipulation. When we're actually talking about circuits, the waveform travels slower than the speed of light. And we have a thing we call velocity factor, which you'll see when we talk about coaxial cable or even wires. To figure out the wavelength, you need to know what the velocity factor is. In other words, what percentage of the speed of light is it actually traveling at through that conductor? In coaxial cable, sometimes it's as low as 0.75, the speed of light. So you need that correction factor, or else your length measurement for the wavelength is off. And in fact, one of the exam questions, you can get the right answer without doing the correction factor, but it'd be close enough that you can guess the right answer. But without, if you use the correction factor, you get the same answer as on the exam. And they're using 0.95 for the correction factor for a normal copper wire.
So is the correction factor given on the exam, or where to know?
In that particular question, yes. Or it's built in. There's another formula, which I didn't put on here. Use 468 divide the wavelength times the frequency, or use those. And the answer comes out in inches because they've already factored the conversion factor in there, and it gives you inches for half a wavelength, which is another one that's commonly used. Because when we talk about antennas, typically you're going to talk about a quarter or half a wavelength. So they use that one because a lot of people like to deal in inches. But it's easy to, if you do it in meters, it's easy to convert. Remember, just assume 40 inches per meter. Okay, so alternating current continuously changes direction At a frequency is the number of times it changes per second. We normally use a small f to represent the frequency, and we do it in hertz. And we have hertz and kilohertz and megahertz and gigahertz, and then I don't know, terahertz, I guess. I don't deal in that frequency here. We have the phase, okay, where it can be shifted, and you'll see with inductors and capacitors, they create a phase shift. And then wavelength is the distance that it travels during a cycle, based on the speed, which is the speed of light or less, depending on the actual medium it's going through. Okay, reactance. It's the opposition to AC current flow by either an inductance or capacitance. Capacitor or inductor. And they behave differently with AC current. So if it's a capacitor, we call it capacitive reactance, and it's inversely proportional to the frequency. If it's inductive reactance, it's going to be directly proportional to the frequency, which means the higher the frequency, the higher the opposition to current flow. Whereas capacitance, the opposition to current flow is less the higher the frequency. Okay, so the formula for capacitive reactance is one as a reciprocal of 2 pi times the frequency times the capacitance. So there's our 2 pi radians times the frequency. Okay. So that product is the number of radians, circles per second times the capacitance. And here I did a simple resistor capacitor, put a sine wave on it, and varied the frequency. And it goes from 1 hertz up to, I don't know, that was blocked, but fairly high frequency. But you see, the reactance starts fairly high and decreases as the frequency goes up, and it decreases exponentially because it's a reciprocal. Whereas when we do the inductor, it's just the opposite of this, so it will be a straight line. And we got the old Eli the Iceman again to show the phase shift. And we plot the reactance on the negative complex plane. The complex plane is where you plot real versus imaginary on a rectangular plot. So below the line is negative, and that's capacitive reactance. Inductive reactance will be on the positive side. So inductive reactance is the same formula, except it's not a reciprocal. And you substitute L. It increases with frequency, and this would be a straight line if it wasn't a logarithmic scale. But because this is a logarithmic scale, it makes it look like a curve. And, you know, we plot it on the positive complex plane. Okay, so reactance is the opposition to AC current by inductance and capacitance. Pretty sure that's a test question or something like that. Capacitive reactance is 1 over 2 pi FC. Inductive is 2 pi FL. And you got the phase shift depending on whether it's inductive or capacitive. Goes 90 degrees one way or the other. Any questions on reactance? We'll come back to it on resonance. Everybody good?
Good. I'm gonna have to scoot.
Huh?
I have to scoot.
Okay. We don't have much more.
How long?
Let's see. Well, I hate to guess. I think it's just this and resonance. Okay, so transformers are made up of 2 or more inductors or coils on a common core, which could be air or more than likely some powdered iron or ferrite material like a toroid. That means that they share the same magnetic field because all the magnetic lines of force are all concentrated together in the coil. There's 2 coils or more on the same thing. So they have the same magnetic field, and we call that mutual inductance because they interact. We have what we call a turns ratio with 2 windings in a transformer. We normally call it a primary and a secondary. You have a number of turns on the primary and a number on the secondary, and the ratio of those is what we call the turns ratio. So if you're doing what we call if you had a 1-to-1 transformer, which you were just using for isolation, and a lot of times you'll see that in AC utility power used to isolate grounds, it'll have a 1-to-1 turns ratio. So the same number of windings on both sides. There's no voltage increase or decrease. If it's a step-up transformer, okay, you're going to have more turns on the secondary than you do on the primary. So the primary turns is going to be less. And that ratio will determine how much the voltage is multiplied by. So if it was a 1-to-2, it means if I put 120 volts on the primary, I get 240 volts on the secondary. However, when I do that, whatever current I have on the primary is going to be halved on the secondary because the power into the transformer, assuming no loss, is going to be the same on the output. So whatever the input power is, the output power is going to be the same, even though the voltage and current will be different.
So you're gonna run, let's say, 120 in at 100 amps. And then coming out, it would be 240, 50 amps.
Yeah. If that math is right.
Well, yeah, depending on what you're doing.
And a step down is just the opposite. Okay, I'm going to have a lower voltage out, which is what you would have normally seen in older electronic equipment where you got 120 volt AC coming in, and then you want to get, say, 12 volts out. So you step it down to around 12 volts and then regulate it to get 12 volt AC. And in that case, you're going to have more current on the secondary because you got a lower voltage. And this is just a typical transformer circuit with a load with a step-up ratio. And we got the blue is the primary voltage coming in, and this yellow one is the secondary. And this is where 0 is, so you can see that the waveform is twice. Okay. Down here are the currents, okay? And blue, in this case, is the secondary, and yellow is the primary. So you can see that the primary current is higher than the secondary. And also, because of the inductance, there's a phase shift between the primary and the secondary of 180 degrees. There's typical transformers. Again, of course, that's not actually, it only got one winding, but if you had a second winding on there, then it would be a toroidal transformer, like this one. I had trouble finding a decent picture of a lot of transformers. So a transformer is two or more coils on a common core. They have a shared magnetic field, which is called mutual inductance. And the turns ratio is the ratio of the primary to the secondary. And it determines whether it's a step up, step down, or isolation, 1-to-1. So if you've got a step up, you have a higher secondary voltage and higher current on the primary. If it's a step down, you got a lower secondary voltage and lower current on the primary. Okay, impedance, the opposition to the flow of alternating current. So it turns out it's the vector sum of the resistance, which is the flow to opposition to DC current, and the reactance, which is the opposition to AC by an inductor or a capacitor. So this is where we get back to the old right triangle. So we have the resistance on the real axis and the reactance on the imaginary axis. And the magnitude of this hypotenuse is the impedance vector. So, and this angle is the phase angle. So that will be how much shift there is between the voltage and the current. And here I'm just showing how you plot the capacitive and inductive reactances. And the way we learned it in engineering was we always used omega, which is 2 pi f. So it's radians with frequency already in it, just to make it less things to write in the formula. And we can calculate the value of the impedance with the square root of the sum of the squares. Okay. And we plot it as on the rectangular coordinates as the real on the resistance on the real axis and the reactance on the imaginary axis. Okay, resonant circuit. It's an LC circuit. There's a combination of inductance and capacitance. At a certain frequency, it will resonate. He talks about it similar to like a tuning fork. Okay. And what happens is you've got energy stored in the capacitor. Okay. When it gets up to where it's charged up, then that charge decreases and that current starts charging up the inductor. So the energy is going from the electric field to the magnetic field and then back again. And this goes back and forth. If there was no loss, then it would oscillate forever. In order to keep it resonant, like to create an oscillator, you need to provide enough feedback to compensate for the loss to keep it oscillating. Because in the real world, there will be some resistance in both the capacitor and inductor. So you'll lose some of the energy as heat. So it's resonant when both the capacitive reactance and the inductive reactance are equal. and opposite, so they cancel one another. So if you do R plus Jx sub L minus Jx sub C, and if X sub C and X sub L are equal, then impedance is equal to resistance. They cancel out. And that's the frequency that happens, is where it will be resonant. The formula for resonance is the reciprocal of 2 pi times the square root of the product of the inductance and capacitance. That one you need to remember. Pretty sure it's on the tech test. Definitely on the other. Okay, so this little circuit, I like this one because it's showing the energy going back and forth between the two, and current changing direction. This is just an example of if I had a 1 microhenry inductor and a 1 microfarad capacitor, the resonant frequency is going to come out to 159.155 kilohertz. And here's that circuit with a 1 microfarad capacitor and a 1 microhenry inductor. And we applied a sine wave to it. And you can't read it here, but at 159 kilohertz is where, and this is a series circuit, the voltage across these two components goes to 0. And the current, okay, goes from basically 0 up to its maximum value, limited by this resistor and the amount of voltage. And over here is a plot of the impedance, if you calculate it, and this is just 1 divided by the other. So you can see that the impedance goes down to 0 at the point where it's resonant. It's kind of hard to see on that one. Okay, this is a parallel circuit where the inductor and capacitor are in parallel instead of series. And here we have the voltage across this combination, and it starts out at basically 0 or almost, and goes up to its maximum value where it's equal to the input voltage. And you see that the current is going to go to 0 where it's resonant. The difference between a series and a parallel resonant circuit is that resonance, a series circuit, looks like a short circuit, 0 impedance. A parallel circuit at resonance looks like an open circuit or infinite impedance, which you can't ever get infinite because it's real components. And this was a little calculation of, at that frequency, how the impedance changes. Turned out this is what we call a very high Q circuit. So it's a very narrow band where it's resonant. Okay, so impedance is the opposition to AC current flow. It's the square root of the sum of the squares of the real and reactive components. The resonant circuit, test question, is composed of series or parallel LC components. Capacitive reactance is equal to the inductive reactance when it's resonant. There's the formula again, which is the reciprocal of the radians times the square of the product of inductance and capacitance. In a series resonance circuit, the impedance is low at resonance. Parallel, it's high at resonance. So that determines when you're doing a circuit like an oscillator or something of whether you want it to pass a waveform at a resonant frequency or block it, depending whether you use a series or parallel circuit. Okay, Lou. Made it.
I gotta run.
Any questions?
Yeah, do a lot of studying.
Huh?
I have to do a lot of studying.
Just do the practice tests.
Yeah. I think the big thing is just memorizing the formula. Once I get the formulas memorized, I'll be able to do
Yeah.
calculations.
Well, it depends on what you consider the hard part. For me, well, I mean, I've been an engineer for 60 years. None of that stuff was a problem. Some of it I had to refresh for the extra. The rules and regulations are a pain in the butt. Because that's just memorization. Well, not so much that, but lots of rules and regulations, and you don't know why, it just is. So for me, that was the hard part.
Have you looked at the series resonant?
Okay, series resonant. Oh, I don't want to go there. Previous. Okay, this one.
Thank you, I just wanted to look at it.
Did you do the formula? Oh, okay. Yeah, I did these and I'm still learning it. Signed up for a thing called Circuit Lab, which they have a free version or almost free version where you can do this stuff, but they limit you to 10 components. So you're kind of limited as what you can do. But for $6 a month, you have unlimited components. And it'll do a lot of simulation. There's a bunch of them out there. And I've tried several. This is one of the easier ones to use, but it doesn't have some capabilities I'd like to see. But for the most part, it works pretty well and it's easy to use. I mean, you can easily build a circuit. You have a whole list. And we'll do more of them on part 2, where we're actually going to do circuits and talk about transistors and diodes and tubes, just because it's on the test.
Yeah.
And at the end, get into digital logic, but do filters and mixers, oscillators, talk about receivers and transmitters, how they work, and put the pieces together.
I mean, the last time I thought about a lot of this stuff, probably a great technology class for doing this next. So it's been a few years.
Oh yeah, if you don't use it, well, you forget.
Yeah. That's why I try to simplify everything in my head when I do the circuits, I just kind of think of like a light bulb on a simple circuit.
All right.